Hello and welcome to That's Absurd. Please elaborate. This is a podcast.
Yes.
You listen to it. That's what you do.
You're doing a great job so far.
Thank you. This is my 69th time doing it.
Oh, no, I was talking to the person listening, saying that they're doing a good job.
Oh, I thought you were... Okay, anyway.
No.
Well, yes.
You're doing an adequate job.
Oh, B+. Perfect. That's where I'm aiming for. This is a podcast where we answer strange or off-the-wall, weird, ridiculous questions that you, the audience, send us, and we, the two persons who you are hearing, we are sometimes called colloquially the hosts. We answer those questions using as much science research as we can find, if there is any. And sometimes there's not, and sometimes there is. And it's really fun. And if this is your first time, welcome. Thank you for being here. I am Trace Dominguez, one of the two colloquial hosts, as they are called.
And I am the other colloquial host, the +1 to equal 2, or does it, foreshadowing, host Julian Huguet.
Well, then why don't we just jump right into it? So, Julian, who sent you your question, and what is it?
The person who sent this question is Nick, who I now hate. The question was actually chosen by our Patreon subscribers in a poll. It was one of two that tied. It was a tie vote, and I picked the harder one, in my estimation, from Nick, who asks, what if 1 + 1 was 3?
Oh, Nick also did send us an audio clip.
Hi again, Trace and Julian. It's Nick from Pasadena, California. What if 1 + 1 was 3? I hate math, and I want it to change, but I do recognize it has its uses. So, if through secret magics we made 1 + 1 3, how much would break? I assume math would break, as would science. Helium seems primed to have bad things happen to it at the very least. But would it be, bad for our ability to do architecture, because floor plans would be weird now? Would the economy get weird? Would sports scores get weird? How much would just fall apart? Would there even be a 2? I can confidently say that it would not fix anything, but that's really all I've got. So, thanks, Julian and Trace. Have fun.
Oh, Nick, I did not have fun. I did not have fun with this one.
No, I can imagine not.
So yeah, Nick, as he intimates, right, a lot's kind of riding on 1 + 1 being 2. It's sort of foundational to, math.
Julian, for the people that don't know already, what is a 1?
Okay, we're actually going to get to that.
Oh, good.
Because it's actually a lot more complicated than you might think.
Wait a minute. I have one apple. That's what I have a 1.
No, save it, because we'll get there. All right. This has been actually a topic of discussion among mathematicians for a lot longer than I had realized, and doing this research brought me to that. But before we get to a formal definition of 1 and 2, let's just start with our intuitive sense. I think we all kind of know what 1 is, what 2 is, right? When we see one object, we know that's one object. When we see 2 objects, that's 2 objects. So as Nick starts, he suggests something like helium. That could be a problem, right? Mm-hmm. Helium on the periodic table, it's got 2 protons. Well, if 2 can't exist anymore, then helium can't exist, right? You've got fusion happening in the sun, you've got protons smashing together, and eventually they form this slightly heavier molecule. It's got 2 protons, 2 neutrons. What if all of a sudden it had 3 instead?
So we're just making a bunch of lithium now, somehow.
Yeah.
Cool.
You kind of violate a lot of principles that underpin, physics as we know it, like the conservation of mass and energy, right?
You're so
where's
obsessed.
this? I am, because you can't conceptualize it, right?
Really, I can't.
Where would it come from? Are we just suddenly converting a lot of energy to another proton? How? Why? You'd upend how the universe works as a whole.
The
right?
law of Nick. I think that's how. Nick's first law.
Nick starts there with helium, right? And I think that's a good candidate because there's lots of things that we say are, 2 of something.
Yeah.
But it's sort of based on your perspective, on your conceptualization. I have 2 hands, right?
Right.
Except I have one left hand and one right hand.
Okay,
right? So you could say I have two hands, or you could,
one of two. You have a set of two.
I have a set of two. I have two shoes, or I have one pair of shoes.
Right.
Right? That's a pair.
Yeah.
If you consider it as a separate concept, well, then I just have one pair of shoes.
God,
Can I have one pair of shoes? If I buy two pairs of shoes, do they instantly become three pairs of shoes? How does it work?
I mean, to your point, I mentioned earlier having one apple, but what I really have is a collection of multicellular plant cells, and inside of those, millions of other little things. And I hate it. I don't like that.
So, as I mentioned, this idea of like, how do you pin down what one is, what two is, has been discussed and debated for a while. There was a German mathematician, Gottlieb Frege, who asked what counts as two. And he concluded that numbers don't apply to objects, right? But they apply to concepts. So numbers are the concept of how many things are there you can apply a number to.
Okay.
Right? And it all depends on what your conception of this thing is, right? One deck of cards, 52 individual cards. There's so many ways to dice it up. Frege was trying to set out his own foundations for mathematics, and he came up with this idea where numbers are extensions of concepts. So you have like a concept, like the color red, and the extension of that concept is everything that is red.
How Valentine's Day of you. That's when this episode's coming out about.
Isn't that nice, right? So all red hearts, all red roses, all these things are an extension of the concept of red. 7 is an extension of the concept of all things made up of 7 things.
Okay, so all sets of 7. Whatever the set is, it doesn't matter.
Exactly.
It's just 7 is all 7 of those photons, as well as all 7 of those universes, as well as anything in between.
Right. In 1901, Frege was building out this foundation of math from this axiom, right? This universal truth that all concepts have a corresponding extension. And he was about ready to publish when he got a letter from a British mathematician named Bertrand Russell. And Bertrand Russell basically said, wow, this is a pretty good concept here. It'd be a shame if I were to come up with a paradox that utterly ruined it.
Oh, no.
And this
Bertrand.
This is Russell's paradox. He says, okay, well, consider the set of all sets that are not members of themselves, right? So a set that doesn't contain itself, right? And then you have a set that's all these sets. Is that set that contains sets that are not members of themselves, is that set itself a member of itself? I know that's very confusing, but did that make sense at all?
It is confusing, but I sort of get it. You know, it's hard to describe. Let me get this straight. And I want to say, a chat bot to help me understand this a little bit better.
Okay.
A equals 1, 2, 3.
Sure.
The set is 1, 2, 3. A is not in that set.
Okay.
You're saying that, like, the paradox is, how do you account for the A in this?
Well, you take
system?
a set, so you have A equals 1, 2, 3, B equals 4, 5, 6. You have all these sets that are not members of themselves, and you bundle them together into another set.
Right.
Is that bigger mega set a member of itself or not?
Mm-hmm. Yeah.
If you say no, then it is. And if you say yes, then it isn't.
Yeah, and it messes with...
So it's a paradox.
Right? Yeah.
And so this kind of broke Frege, the poor guy.
It basically broke us just now. And we're not even mathy people.
No, we just dabble in this. This was Frege's whole life for quite some time, and it kind of destroyed the man.
Jeez.
Poor guy. So this paradox, along with other things that were happening in mathematics at the time, like the exploration of non-Euclidean geometry, right? Like shapes that don't fit into this ancient Greek philosopher Euclid's principles of how geometry is supposed to work, like triangles where the interior angles add up to more than 180 degrees. Euclid said that is impossible, but if you draw a triangle on the surface of a sphere, then the interior angles add up to more than 180 degrees. That's a non-Euclidean shape. Stuff like that was starting to break mathematics. And Russell is one of the people who tried to fix that. And we'll come back to that later. But let's first focus on this thing of, okay, well, some objects, like my 2 shoes, you can say I have 2 shoes, but really I have a left shoe and a right shoe. It's arbitrary, right? What we count as one thing or 2 things. But I think that Nick hit on something important in his question when he brings up particles. Mm-hmm. And that is that all particles of the same type are identical.
Yeah. Like all photons are the same.
All photons are identical.
Are the same.
They all have the same properties. All protons are the same, all neutrons, all electrons. And then, so long as lithium, you have the same number of protons, neutrons, and electrons all together, it's identical to any other lithium isotope
with those
and ion that's the same.
With that same set, if you will. Yeah.
Exactly. So here we can kind of explore this idea and say, okay, well, this isn't arbitrary now, right? If I have 2 electrons, suddenly, what if I just get a third? Mm-hmm. Well, even more fundamentally than if we start getting to, the larger atoms and elements, this screws everything up.
Yeah. I was going to say, you take 2, well, let's say there's no 2. You have 1 electron, you have another 1 electron, and when they approach each other and somehow become, instead of 2, they just a third electron appears.
Right.
Out of nowhere, quantum style, just like, pew, pops into existence.
Yeah. The reason this would mess everything up, though, is that a lot of our understanding of how atoms interact is based on how the electrons of different atoms interact, and all of that is based on pairing up electrons in orbitals.
Right, yeah.
Right? So when
like
you're taught...
the Bohr model, and I mean, that's a simple way to draw it, but, that's what I remember.
So when you're taught, chemistry in school, you're taught that these atoms are either reactive or non-reactive based on if these electron shells, these orbitals that electrons hang out in, are full or not, right? Mm-hmm. So at the lowest level, the lowest energy state that electrons can be in orbiting around an atom, you have the 1s orbital. And for hydrogen, it's very reactive because if you just got 1 proton and 1 electron, there's space for 1 more electron in there, so it can basically grab an electron for something else, or it can lose its electron and have no electrons in its orbital and be very stable.
Right.
Meanwhile, for helium, the reason it is the first of the noble gases is because it's got 2 electrons filling up that shell, that orbital, and it doesn't need to grab another, and it doesn't give up both electrons at the same time to become stable, so it just is non-reactive. It's inert. That's the same for all the noble gases all the way down, right? Their electron orbitals are full up, and so they don't need to take in any more. Well, you might say as the atomic numbers go up, though, you have new orbitals, like the p orbital, and the p orbital can fit 6 electrons in it, right? So the outer shell of neon, right, the next noble gas down the periodic table, it's got 2 electrons in its 2s orbital and 6 in the p orbital.
Yeah.
And you might say, well, because it's 6 in that p orbital, right? That's fine. That's not 2. But it breaks down into 3 sets of 2. Electrons basically pair up in these orbitals based on spin. You get 1 up spin, 1 down spin electron that can occupy the same orbital, and then you fill up the next orbital and the next one and the next one. So if you think about it, really, all of chemistry is based on pairs.
Right.
Pairs of electrons.
Pairs of electrons, that is to say, 1 electron and another one coming together.
Right.
Not having a third wheel all the time.
Because they just have the 2 spin states, right? They because of something called the Pauli exclusion principle, you can't have 2 electrons in the same orbital, same energy state with identical spin.
Yeah.
So because they have 2 spin states, you get one spin up, 1 spin down. Those 2 electrons can be together. That's fine. They'll pair up, they'll fill up that orbital, and then you start filling up the next one.
It's like a Taurus hanging out with a Scorpio. You know it works? Or I don't know anything about astrology. I just mean
Sure. Might as well be. It's equally valid to all other astrology I've heard.
Yeah, you're right. You're right.
So, sure.
Sorry, astrology people.
I'm not. what that means then, if you suddenly have to have a third electron pop into existence and join this energy state in this orbital, is now we've changed how electrons work fundamentally.
Yeah,
now I guess they can have 3 spin states.
I guess. We got up, down, and none.
Up, down, side to side.
Side to side,
down,
shimmy.
Side to side.
Up, down, and shimmy.
Down, side to side.
Now we got to dance. Up, down, shimmy.
But I think our problem might even be more fundamental than that. Because what are protons and neutrons made out of?
Oh, no. Waves.
Yes. Yeah. Oh, man. I love you so much. You're right. But when we think of the subatomic particle, right?
Right. Okay.
Because everything's a wave, it's essentially a wave. But it's like a little packet of energy, right? A little wave in a field. What are these subatomic little particles?
Yeah, you've got the quarks.
The quarks. That's right. So
you got the strange ones and the charming ones and the ups and the downs. Wait a minute, these all come in pairs too!
Oh, no!
Oh, no!
Oh, no! Right?
Up and down and charm and strange and all the other ones.
Top and bottom are the 2 remaining, right?
Yeah.
So protons and neutrons are not the most fundamental particle. They're made up of even smaller particles called quarks. And protons, neutrons, they're made up of 3 quarks. So, dodged a bullet there, right? They've got 3. Except they're made up of, for a proton, 2 up and a down quark, or for a neutron, 2 down and an up.
Right.
And like the other particles that are larger than them, or like electrons, they're all identical, right? They have the same properties. The only difference with quarks inside of a proton or neutron is their color. So these things have, quote unquote, a color, but really that's just a way to help us think about how they interact, right?
Yeah.
When you've got a proton with its 2 ups and a down, the colors, quote unquote, of those quarks are red, blue, and green. So when you combine those colors, like when you combine red, blue, and green light, you get white. So this idea that these teeny tiny subatomic particles have a color is called quantum chromodynamics.
Okay.
And quantum chromodynamics states that you can have all sorts of weird particles so long as the quarks that make them up produce white. So you can have red, green, and blue, like you do for protons and neutrons, or you can have weird other combinations, right? These are all, by the way, hadrons. Everything that's made up of quarks is a hadron. When you hear the Large Hadron Collider, that's what they're talking about.
Been there. It's cool.
I'm so jealous. I hate you so much.
I've been there twice.
Stop it! So these things made up of these 3 quarks are baryons, but then you can have mesons that are made up of 2 quarks, right? And you can have like red, and what's the opposite of red?
Green.
Anti-red.
Oh, no!
or cyan, right? Or you can have, blue and yellow, or green and magenta, but you might call them blue and anti-blue. And so you can have these mesons that are 2 quarks. You can have tetraquark particles that are made up of weird, combinations of all these. You can have pentaquarks that are like red, green, and blue plus red and anti-red together. So it all still cancels out to white. So my thinking, if we're following Nick's line of logic, that you can't have 2 of something, quarks included, is that all of a sudden, all the matter that makes up the universe, in order for it to exist, has to be exotic. It's not like the baryons that you and I know anymore.
Yeah.
And the problem with that is stability. We have found a tetraquark in the Large Hadron Collider that lasted a shockingly long time, 10 to 21 seconds. That's it.
That's still a long time.
That's the longest lived tetraquark particle that we've seen. It was discovered in 2021. We think there could be stable configurations with 4 quarks, but we haven't found them yet. However, and I'm no particle physicist, so I don't know what the stable configuration could consist of, and if it doesn't have a pair that would violate Nick's rule.
Right.
But the one that we found in 2021 that was stable for 21 seconds, it had 2 charmed quarks as part of it. 2 charms, an anti-up and an anti-down, to be specific. So that also would violate Nick's rule.
Yeah. Dang it.
I know. So before we even get to, macro scale stuff of like everybody's got 3 hands and shoes are all in 3s and you can never have 2 of any object. Frankly, the universe itself would look completely different if it could even form stable particles at all.
Wow.
Yeah.
I mean, I don't even know. It's like overwhelming to think about all the things that would not work.
It is.
Because it's like, I don't even know what to say. This might be our most overwhelmingly confusing question ever. So thanks, poll, for voting on that one.
Good job. Love you. Okay. Happy Valentine's Day.
Happy Valentine's Day.
That kind of gets to the fundamental issue here, and that is math isn't like other fields like, biology, where we can observe things and make deductions on how they work. Math just seems to be true by definition. Right?
Yeah,
1 + 1 = 2 is a truism because that's just how it is. There's kind of no easy way to describe it. But people have tried. And this brings us...
tried to describe math.
Yeah, people have tried to describe exactly why the fundamental logic in airtight, unassailable terms of why 1 + 1 = 2.
And it's not just 1 + 1. It's not just 2 apples means you could have 1, 2, 1. Well, I'm broken.
See, you're running into the exact problem of trying to define it intuitively, right? Of course 1 + 1 is 2. But when I ask you why, all you can really do is go, because it does. Because it does, right?
There's 2. I've got 2 of them, and before I had 1 of them, and now I have 2 of them, and it's 2.
It's 2. I don't know.
I don't like the person who asks me that. We're not friends. This is a Wendy's. Do you want a 4? Do you want a 5-piece, or
can you imagine ordering at a Wendy's and you're like, I'll take a number 2, and they go, what is a number 2? Like, what is the concept of 2?
I would just say a number 2 is a Dave's double.
Right, but that's 1 patty plus 1 patty. But why is that 2 patties now?
But why?
Right.
Ugh. Wow. So, yeah, I would leave and go to Taco Bell.
The official...
Where things come in 3s, because I get 3 supreme tacos. 3. And 1 Mexican pizza.
Taco Bell hates the concept of the number 2.
Maybe they do.
You see, go look at their menu. There is no 2. How much business do you think we're driving to Taco Bell?
None. Negative business.
Okay. So this brings us back, though, to Bertrand Russell, the guy of the paradox from earlier who ruined poor Gottlieb Frege. He and another guy, Alfred North Whitehead, in the early 1900s, they were seeing that mathematics was in this precarious position. You had the Russell paradox, you had non-Euclidean geometry, and it seemed to be the very foundation of math was in danger of crumbling. And by the way, huge shout out to a couple different people. First of all, there was a channel that I found called Up and Atom, hosted by Jade. She made videos on this.
I love Jade.
The Russell paradox. They're fantastic. I also want to shout out our Patreon subscriber, Win, who sent me a little, as soon as the poll result came in that 1 + 1 = 3 was going to be the winner, she was like, you might want to check out this video on Bertrand Russell. And I was like, that's fantastic. Thank you, Win.
That's awesome. Also, Jade is a Nebula person, so you can watch her videos on Nebula. We'll tell you more about that later.
Perfect. So Jade, in her video, talks about how Russell and Whitehead sought to build this concrete foundation of mathematics. And they wanted to do it using symbolic logic, right? Using logical statements that were 100% unassailable, no contradictions, no paradoxes possible, right? Something like, if P is false, then P is true. That sort of stuff. I took a symbolic logic class in college and I really loved it. Everybody else seemed to hate it, but it just was like word puzzles. So that's...
I mean, what you just said makes total sense to me. If the whole class was like that, I think I would get really upset
I took it for fun, by the way. Everybody else was taking it and they were just hating it. And I was like, what's this? This looks interesting. Was not part of my major, was not a GE. It was like, oh, cool.
That's
Symbolic
very
logic.
Julian. That is an extremely Julian thing.
I know. I've forgotten all of it since then. Yeah. Other than things like, modus ponens and modus tollens, which are like the descriptors of, these ways that logical arguments are built and how they lead from one conclusion to the next to the next. That's what Russell and Whitehead set to lay out as the foundation of mathematics. And they wrote a 3-volume book called Principia Mathematica. First volume came out in 1910. I found a PDF of it. It's 722 pages long.
So you read all of them?
I did, in preparation for this podcast. I think they even joked, or some publisher joked that it's so dense and so long and so confusing, maybe 6 people will read it,
Wow.
But they spend a lot of time explaining what they're doing, laying the foundation of how symbolic logic is going to be used in the book, how it all works. And by page number 359 is when they introduce the concept of 2.
Wow, it took that long. On a 722-page book, it took them until halfway, essentially. Halfway to get to the concept of dose.
Yes, just what 2 is. And they try and use the idea, once again, of sets, right? They imagine it like, okay, if you're going to explain what 1 is, what 2 is, you can't, as Jade says in her video, hold up like one finger and say this is 1, because somebody might interpret that as, oh, a single finger is 1, right? Or anything you hold up, right? If you say like, this is 1, they'll be like, oh, that specific thing is 1. So it helps to think of 1 as the set of all sets that have a single element, right? 1 finger, 1 capybara, 1 Xbox controller. I'm just looking around the room. I don't have a capybara.
You have a capybara there?
No.
1 apple, 1 Julian, 1 universe.
Yes.
Of stars.
Uncountable stars.
Right. Just the 1. It's just a 1.
But it's one thing. Right.
1 universe.
So it takes them that long to build up to, 2 is the set of all sets that contain 2 elements, this many elements.
So they spent the 358 pages prior to that really digging into what a set is, how the argument that they're making is functioning. That rhetorically I can totally understand that would be very complicated to explain and could take a little while.
Yes. And so it takes them that many pages to get to 2, and then just a few more. They're so close. It takes them till 362 that they have a proof using all this symbolic logic that they've established to show that 1 + 1 equals 2.
So let me see if I get this straight and tell me if I'm wrong or stop me if I'm off track. 1 is the loneliest all number of the sets of all of the the ones, basically, all of the sets of things that contain one thing. Then another, somehow, set of all of the things that contain one thing together would be 2 sets, each containing all of the things that are one thing.
I think that's right.
I don't know. It seems right, but also... They also
had to do the hard work of like explaining what addition is and what equals. I don't think they actually explained what addition is. I think they were going to do that in a later work and just never got around to it. They had to explain what equals meant, right? And that again was comparing sets. Like if you have a set that has this many things and compare it to another set that has this many things, they are equal if you can pair them all up and no things are left over. That's the kind of detail we're talking here. To prove that 1 + 1 equals 2. Which I just found as a sort of side note, just fascinating how when people dive into mathematics, what a rabbit hole they can go down. And Whitehead and Russell wanted to build up this entire, complete system from Principia Mathematica until another mathematician in the 30s, Gödel, basically showed with a proof that you can never have a complete system of mathematics that doesn't contradict itself in some way and kind of ruined all their work. Yeah. So anyway, to get back to Nick's question, though, what if 1 + 1 was 3? Apparently, because of the work of some absolutely mad mathematicians in the early 1900s, we've shown that cannot be possible. It only took 362 pages to do it. But If it were, you'd break physics completely. You'd break how we understand how everything works. You'd break what the universe is made up of. Yeah, and you'd break, obviously, mathematics.
I mean, it wouldn't be just bad for helium. It'd be an everybody dies TM situation.
Yeah, well, what I keep coming back to is if this were true, if 1 + 1 = 3, the only thing I can imagine then is somebody would have to be determining what counts as 2 and then making the decision to add a third thing in.
Yeah.
Does that make sense? There would have to be some unaccountable force, entity, something.
Right.
That doesn't play by any rules except the ones that it arbitrarily decides, right? It would be it would break kind of how we understand science, right? As this idea that we're
like an
building
objective,
objective systems and rules that we believe our universe is governed by. It would ruin that. You'd have some non-accountable figure calling the shots.
Be like, that's 2. That's 2 now.
I've decided
it can't
that's
be
2.
2. Yeah.
Can't be 2. That's 3 now.
I can picture a physics in my head where it's like, no. There's just nothing stable in pairs. Everything is only stable in triples. You need 3 particles or 3 waves or, 3 vibrations of string to make something that would be stable. Sure. I guess there could be a universe where but it's not very simple. Like it's not the simplest way to make a universe. And so thus seems really unlikely that a universe would just spontaneously come into play that has to have 3 things in order to be stable.
Also, stability is not the same as not existing, instability, right?
Yeah.
Like I said, we've found tetraquarks, pentaquarks. They are not stable. They decay very quickly.
Yeah.
But they still existed at some point.
Yeah, for 21 seconds or whatever.
Yeah, at most, Yeah. Sometimes it's down to like femtoseconds, the incredibly small measurements of time, but still, they were there.
They existed. Yeah, it's we've never had a question that broke us or the universe quite in this way, so thanks,
I don't know.
Nick.
I remember an early one from Cliff about turning off the 4 fundamental forces, and it was a similar idea, right? Like
that
these
one,
things that we've built everything off of because they're, observable and they just seem to work that way. And if you turn them off, like everything that you know and understand gets upended because they are the complete underpinning of the universe.
Yeah. Well, with that, why don't we take a break and everybody can just breathe for a minute, clear your mind, and we'll come back with some silly animal stuff.
Yay, capybaras!
Julian, give me your best dinosaur roar.
Oh, God, an asteroid! It's horrible!
Wow, that was not where I expected that to go. We're popping in before the show to tell you about I Know Dino. It's a dinosaur podcast.
We think of those dinosaurs being this thing that's been dead for tens of millions of years. Even so, studying dinosaurs can still teach us stuff that is relevant to the world today.
Yeah, like climate models to help us understand global warming.
Migration patterns of dinosaur lineages. They tell us about Earth's changing continents.
We can also study dinosaur diets, what plants lived then, and maybe what animals and how they interact.
And, this is super cool, many dinosaur injuries, paleopathologies, they're the first known occurrences of diseases.
And they talk about all this kind of stuff on I Know Dino. It comes out every week with new dinosaur stories that you're not going to hear anywhere else. Like, I hadn't heard of a lot of these, which is pretty cool.
You can find I Know Dino on Apple Podcasts, Spotify, wherever podcasts are. And if you found us, you can probably find them. Go check them out. Hello and welcome back to the second part, the 1 + 1 = 2 part of the episode.
No, this is the third part. This is the third.
No,
third part.
This is just third.
There was no second. There's no 13th floor.
Just always say that it's the third part.
Yeah.
I was like, wait, did I skip the second? It's like that prank where you release like 3 pigs at your high school, but you number them like 1, 2, and 4.
Oh, good prank.
Where's the third pig?
Yeah.
Exactly.
Something I didn't think about in your answer. Would that mean there's no letter B? Like, what about anything?
What counts as 2?
Yeah.
Trace, what counts as 2?
That's a weird way to phrase that if you speak 2 languages. Please continue.
Anyway. Well, Trace, what is your question this week?
My question this week comes from Adam, who asked, also in a poll, and also selected by our patrons in a tie. This is a double, again, question episode where both questions were voted upon by our patrons.
Now I'm just going to see twos everywhere. Thanks, Nick.
Oh, sorry. This is the third episode, but really the second. I'm sorry. The B episode? I don't know.
The third question in a three-way tie of 2, 3.
What is the most spherical animal?
Ooh.
And Adam elaborated, vertebrate and invertebrate categories are acceptable. I think round critters and fat pets are adorable.
Aww.
I watch Rollin' Safari on YouTube. Is a pufferfish the most spherical? A desert rain frog? Yeah. Have you ever seen Rollin' Safari? I'd never heard of this.
I have not.
Rollin' Safari, if you're driving, don't look it up. But if you're not driving, it's very cute. You go look it up. Basically, it's animated animals that are made into little balls, and they roll around. And it's cute and funny
how do you spell
ridiculous. That? Rollin', Rollin, Safari.
Okay.
On YouTube. So
Rollin'
very interesting.
Safari. Aww.
Yeah, it's like very cute and funny and
puffy guys.
I was unawares of this channel, and I am now awares, and thank you for that, Adam. If nothing else, we can take that away from this episode. But they're all literally animated animals. None of them are about like round animals. And so it reminded me of this old physics joke, actually. Milk production at a dairy farm was at an all-time low, so the dairy farmer decided to call on the local university for help. Have you heard this joke, Julian? I feel like you've heard this joke.
No, I haven't.
A team of the institution's top scientists was assembled to work on the problem. The team of scientists visited the farm and took extensive data, carefully examining every step of the production process. The leader of the team, a theoretical physicist, offered to write the report.
I haven't heard it, but I see where this is going.
A week later, the physicist returned to the farm. What did the physicist say?
What?
I found a solution for your problem, but first we have to assume a spherical cow in a vacuum. That joke kills at the physics conferences, yo!
Perfect. Love it.
Yeah. So for those that don't physics hard as apparently we do in this episode, I'm sorry about that. A lot of physics is about getting close to the answer without necessarily needing to know the exactness of the answer every time. So maybe you're designing some experiment and you have to make an assumption, like, for example, gravity doesn't exist, or we need to make a black body, is involved so that we don't have to actually measure some radiation. You have to just make a lot of assumptions. And one of those is assume a spherical object in a vacuum.
Right.
It's a classic physics
Classic.
assumption. And because spheres in general don't really exist in a perfect way, like even planets or oblate spheroids. And it's just like the most spherical star ever found was discovered not that long ago. It's pretty cool. It's literally just mathematically very spherical.
Oh, wow. I could just see the astronomers crunching those numbers and getting the result on how close it was, right?
Yeah.
Some decimal point number of how close it is to a perfect sphere. And they're just like sitting back and going like, wow.
Whoa. Yeah.
Wow,
Dude. Jared.
You gotta see this.
Jared, Kelly, come here. Come here.
Look at
Look at this. And they're literally just scrolling through some like Excel CSV. And they're just like, look at that. Look at that. And they're just like, whoa.
How close it approximates a perfect sphere. And they're like, wow.
That's when you find people who match your freak. So,
nerds. Love 'em.
Yeah. The point being here, I bring this up because if I say like make a list of 5 animals and want to know which is the most spherical, it's going to be a mess. So instead, I'm just going to address spherical animals in general and try and find the most spherical. But I think I've broken Adam's theory a little bit. Pufferfish is what Adam brings up. And actually, it does make sense, right? Pufferfish are quite round. They do just inflate themselves. We talked about this on the podcast before. They suck in a bunch of water into their very stretchy stomachs, and they stretch themselves out. If you've seen a pufferfish before in a cartoon, like Finding Nemo or any other cartoon, they're definitely round. Super sphere-ish, which is good on you, Adam. They do this, by the way, by buccal pumping, which is cool. Really neat. They can swell 3 to 4 times their normal size. The smallest pufferfish, just a few centimeters. The largest are over half a meter, like 2 feet long, puffing up into a big old ball. Really cool. It's a short-term defense mechanism, though.
Right.
They can't like swim very well. It uses a lot of energy to hold it all in. So it's just like, get away. And then they hold it for a little while and they have to let it go and they've tired themselves out. Humans, by the way, let me just take a quick sidebar. Humans don't really think about stuff like that. The fact that this is really hard on the pufferfish to do the puffing. Like you see a pufferfish in an aquarium, what's the first thing people do? They go like tap on the glass and try and scare them and make them puff up. And like that is really hard for them. It could hurt them. Like if we say, just to pick something at random, drag a fake seal behind a boat so that a great white shark might jump out of the water and get this spectacular shot for TV week about sharks, or have a gazelle run away from a big cat, those animals had to use energy to do that. It's not just like they can do that as many times as they want. Maybe the shark that jumped out after that fake seal, this was their very last amount of energy. They're just like so tired. They haven't eaten and they're like, oh my gosh, a seal. I gotta get it. And they don't get it and then they go and die. That's so sad, but that could happen.
Making me really bummed out now about all these nature
These are real
documentaries.
Animals, okay? They're real animals. Okay. Most documentaries have ethics where they don't do stuff like this. Not all. That big cat didn't catch the gazelle, which was very, yay, the gazelle, it made it back to its mom. But also that big cat didn't eat now.
Katie and I watched a documentary, I think it was called The Hunt on Netflix. And it was all about, predators trying to catch prey. And I think I can count on one hand throughout the entire multi-part series the number of times the hunt was successful.
Yeah.
And it actually made me really bummed for the predator. Almost every voiceover at the end of the segment was like, if he doesn't catch food soon, he'll die. And then it goes on to the next one. And you're like, oh my gosh.
Yeah. I mean, there's a reason. It's funny because we know these things sometimes inherently. Oh, well, a wolf can maybe only have one meal in weeks or something, and it just holds it in his stomach. Or like a snake eats this huge meal and then may not eat again for a long time. And we kind of just gloss over that. Like, oh, that's too bad. It's probably just not hungry. And it's like, no, it's hungry. It's just trying to eat. It's just, you can't just go to the grocery store. Anyway, rant over.
Okay.
My point being,
be kind to the pufferfish.
Be kind to the pufferfish. Don't do that.
Don't freak out the pufferfish.
Don't tap on the glass. Spherical animals. What was the very first animal you thought of that wasn't a pufferfish, Julian? Because I know what
I didn't realize that Adam suggested rain frogs, because I thought of rain frogs.
Oh,
when
cool.
we first talked about this question.
Yeah.
Love those little guys. They're so cute. They look grumpy all the time. They're little balls, and then they turn around and they have like a little butt. You ever seen just like a little rain frog butt?
Like a little tushy.
It's really cute. Yeah.
Are you Googling it now?
I am Googling rain frog butt.
Rain frog butt.
And I'm just seeing.
Oh my God, look at that little booty. Look at that. Please download one. We can put it on our Instagram for this episode.
Love those.
So the first thing I thought of, Julian.
Yeah.
Birds.
As spherical?
Yeah. Do you know what the Audubon Society is?
Yeah, people who drive real fast.
Nice. The National Audubon Society is one of the oldest and most effective bird conservation organizations in the Western Hemisphere. It started in 1905. This is according to their website. And you'd think it would be stuffy, but nay, Julian. Nay. In the parlance of the 21st century, no, 20th. In the parlance of the 20th century, I might just be an old Weisenheimer, but I thought finding a spherical animal would be duck soup. But that Audubon Society, they have things like the bee's knees, got it? So shut your yap and listen to these two periodicals I uncovered. How was that?
Thank you for putting me in the mindset of the 1940s and 30s. My body is ready now.
I'll read the titles for these blogs, which they could not have even imagined in the transatlantic accent era. When is a bird a burb? And an extremely important guide. And what is the difference between a borb and a floof?
How much of these are like internet goofy words and how much are technical terms?
I'm just telling you, the Audubon Society, the oldest and most effective bird conservation organization in the Western Hemisphere, wrote an article called When is a Bird a Burb? And what is the difference between a borb and a floof? And so I thought, because the first thing I thought of is borbs. The borb. Good old borb. And according to the Audubon Society, again, the oldest and most effective, one of the oldest and most effective bird conservation organizations in the Western Hemisphere. Of course, if you can't have two, you can't have hemispheres.
Right. I didn't even get into fractions. Can you have 1/2 of something? Sorry, let's not go back
Jesus.
there.
Oh, no. Okay, so burbs are small, round, and rather cute. Borbs are those birds that carry apparent roundness to an extreme extreme, and most burbs can be a floof. It's just about their mood. So, suffice it to say, I figured one of the most spherical animals might not be a fish like a pufferfish, but a borb.
Okay,
right?
Sure, yeah. I've seen some borby birds.
Yeah, I've seen some borby birds. So Asher, who wrote this blog post at the Audubon Society, wrote some very important rules in their guide about burbs. They are often, though not conclusively, small, often, though not always, round, and appear cute. And the subreddit Burbs defines burb as any bird that is funny, cute, or silly in some way. The Urban Dictionary has a broader definition. And in Asher's second piece about borbs, they went on to talk about how the key and sole criteria for a borb is roundness, which makes sense when you're looking for spherical animals. However, most of the time when you see pictures of borbs, it's not really just the bird. It's the bird floofing. You know what a floof is?
No, but I assume you're going to tell me.
A floof is when the bird puffs itself up, usually to like get air under its feathers because that's how they stay warm, or they're like for grooming purposes. They floof right up. And I think of floofing sort of like I think of the pufferfish getting the buccal pumping and like for the defense mechanism. And I think, honestly, it shouldn't count.
Oh, because it's like a temporary state?
It's a temporary state.
Okay.
We're not talking about temporarily spherical animals. The question is very specifically, what is the most spherical animal? Not the animal that can achieve the sphere the most.
Right.
The animal has to be spherical, not
all sphere all the time.
All sphere all time. Yeah. Same sphere time, same sphere channel. So, technically, the pufferfish is just defensive underwater floofing.
It's an imposter sphere.
Yeah. Dear Tapers, I am not a bird or an animal expert, so I emailed somebody who is.
Fantastic.
Dr. Kadambari Devarajan, an ecologist, conservationist, science communicator, and National Geographic explorer from the University of Rhode Island. She very kindly wrote me back because all of those things are awesome and way cooler than me. They wrote, the first one that came to mind is the pufferfish, which was already in your list. You could check out the Japanese dwarf flying squirrel, the Siberian flying squirrel. There are several birds that are balls of puff, like the bearded reedling, hummingbirds, guinea fowl, some owls, and nightjars also look like cotton candy on a stick. Whale, whale, whale. Based on this rule that we just made up, most of those are only temporarily floofing.
Yeah.
I didn't actually know about this rule when I emailed them because I just made it up like the other day after I'd already talked to her. So.
They're spheres maybe half the time. They're hemispheres.
I mean, or 1/3 of the time.
Yeah, right. Sorry. Forgot our rule.
The Japanese dwarf flying squirrel is very spherical sometimes when curled up, and lots of pics on the internet are super cute, but not ecologically accurate. The Siberian flying squirrel is the same. I also looked up like the ball python. It's right there in the name. Curls up into a ball, but it's really more of a heap. Not really a ball. Should we call it the heap python?
Heap python. Well, no, I thought it was called ball python because it goes to a lot of big parties. Like a big fancy,
Yeah, I didn't look that up.
Yeah.
I mean, I do know that Brittany took that python to a party for sure. So like, if that
That was a ball python then.
I mean, maybe it was. Maybe it was just a Grammys python. I'm not sure. Then there's the mola mola, also known as the ocean sunfish, the award show python.
What? Mola mola's flat.
They're flat.
They're so flat.
They're also circular, though. It looks Latin for millstone, but it's not a sphere. Then there's the silky anteater. I don't know if you look this little fella up.
What?
Oh my gosh, you're going to enjoy it. World's smallest anteater. 400 grams, about 35 to 45 centimeters, 14 to 18 inches, including its tail. It's solitary, has soft, dense fur. It's found in silk cotton trees, and it uses its tail as an anchor and stands on its hind legs. And it's like, me. And it curls up into a ball when it senses a predator.
It's very cute.
And then you got armadillos and pangolins, and they can also spherical up.
Hedgehogs.
Yeah,
pill
exactly.
bugs.
There are all these things, but they're all temporarily spheres. And I really wanted a spherical animal, like a chinchilla, very round, but, not always. And so I ended up kind of thinking about it more, like offline, just like thinking about it for a while. And spherical shapes in the natural world are pretty rare in the animal kingdom,
Right.
In part because of a couple of things. First, the square cube law. We've talked about it a bunch here on the podcast. As size increases, volume grows faster than surface area. Most of these animals either need to absorb heat or get rid of heat. And if you have a round thing, it makes that much more difficult.
Yeah, that's maximizing volume while minimizing surface area. That's the thing of spheres. If you could package like soda in the most ideal way as a manufacturer, if you wanted to use the least material, you'd make a spherical can. You know?
That'd be awesome. I'd drink that.
Yeah, it would be. But then for packaging and shipping, it's bad.
Yeah,
right? So
because you end up with a lot of empty space.
The cylindrical can shape is a compromise then. It's using minimal material while making packaging and shipping as easy as possible. Like having the least amount of space between the cans. Fun fact for you there.
Cool. I think packaging is fascinating.
It is.
So, yeah, you wouldn't be able to move your heat from your voluminous insides. There'd be just so much of your insides and so little of your outsides. And so that doesn't make sense for a lot of animals. Thank you.
Sounds like a compliment. My darling, your insides are looking voluminous this evening. Oh, thank you. It's the ball python.
It's my award show python.
It really highlights my voluminous insides.
Yeah, so stupid. You threw me off, but I love
Sorry.
it. No, it's good.
It just hit me really weird. Just the way you said your voluminous insides. I was like, oh.
You really felt that way. Did you need a compliment today?
I got my insides volumized last week, and nobody said anything until today.
Wow, where do you go for something like that?
Yeah, who's your inside volumizer?
Voluminizer? Voluminist. Voluminist. Wow, the Voluminist is a good band name.
Good band name.
Okay, so I had this in my notes to ask you a question now because I figured I had been talking for a while. So I'm just going to, and then like, well, not really now.
No, it's fine.
Okay. Have you heard of cephalization? Something maybe you remember from Katie's biology classes, perhaps?
Cephalization? I mean,
I had never heard of this concept, but I figured you might have.
It sounds like it has to do with forming a head.
Yes, exactly. It's the evolutionary trend toward concentrating nervous tissue, like the mouth and the sense organs and things, toward one end of an animal. It's an evolutionary trait, or trend rather. So some organisms are strongly cephalized. Like if you think of us, most of our nerve tissue is in our head. And we have nerve tissue elsewhere, of course. But like your eyes, your nose, your ears, your tongue, your mouth, your brain, all in one place. Vertebrates, arthropods, cephalopod mollusks, octopus, squid, cuttlefish, lobsters, ants, spiders, humans, amphibians, birds. These are all cephalized at different levels. They have like strong cephalization and like weaker cephalization. And this is when I thought, maybe I'm looking in the wrong place. Because cephalized means you have to pick an end, which is the opposite of spherical. So once I learned the word cephalization, then I could start looking for animals that were either weakly cephalized or not cephalized at all. And of course, you end up with a lot of like microscopic animals, technically like the Volvox green algae, not an animal. It's an algae. They form these hollow colonies of hundreds of thousands of cells, and they are very close to being spherical. And they just end up that way because it's the most efficient. It's really, really cool. There's the Theomargarita namibiensis, which was discovered in 1999 in Namibia. Its name means the sulfur pearl of Namibia. It's the largest bacterium ever found at the time when they were discovered in the late 90s. It's visible to the naked eye, but it's one bacteria. It like lives in the sediment off the coast of Namibia, and it absorbs sulfides in order to survive because there's no oxygen. It's anaerobic. So what it does is it eats nitrate, which is really cool. So it can use that to kind of your point from before. It doesn't have oxygen to strip electrons off of things to make energy. So it eats nitrates and like uses that to strip out from sulfide, which is so cool. Those are all round, but they're not really animals.
Right. It's bacterium, you said, the Margaritaville one.
Yeah, the Margaritaville one. So then I thought, what are the like lowest cephalized thing that are still in the animal group? Starfish.
Oh.
Jellyfish. Sponges. You can get some round stuff in the oceans. Let me tell you. That's like when Bob Hoskins in the iconic role of Mr. Smee says, lightning. just struck my brain. From the documentary Hook. Maybe you've heard. I don't know. Anyway.
Right. It's been a while.
Echinoderms. Starfish are echinoderms, but so are sea urchins.
Oh, I love echinoderms. You've got sea stars, right? Marine biologists get annoyed when you call them fish. But they're related to sea urchins, sand dollars. Yeah, all those things are part of the same group.
And when you picture a sea urchin, what do you picture?
It's like a spiny little
ball. Right.
They're like those little black puffs from my neighbor Totoro.
Yeah, I got one right here on my behind me.
But like underwater and consuming kelp forests.
So they're typically round, globular invertebrates, which are found on the seafloor of all the world's oceans. They have spines attached to the calcium carbonate skeleton. And if you take those spines off, by the way, don't do that. They're venomous. Don't touch them. But if you do, they look like a ball.
Yeah, they're round.
How spherical are they, though? There is a paper titled Tests and Jaws Morphological Patterns of a Regular Sea Urchin, Paracentratus lividus. And they looked at 256 individuals of that species, the Paracentratus lividus, and they measured a hemispherical index, a height to depth ratio. The closer to 1 is round, and the max sample, like the one in the 256 that was the closest to round, was 0.63.
Okay, so it's more than half spherical.
It's pretty darn spherical, and it's that all the time. It's not just floofing that way. It's just that's its life. I postulate that there is not a thing that is always that spherical, more so than the sea urchin.
Okay. All right. I think, first of all, I love that we talked about the astronomers having like some calculation for spherical and it being like, oh, just a decimal point that's close to sphere. And then it turns out later in the episode, some marine biologists did exactly that.
I didn't even realize that.
And that's
so funny.
Really funny to me.
I didn't even realize.
I feel like we read too many scientific papers when we basically know exactly how they're going to go about determining the sphericalness of something.
I did look up, yes, I was looking for a ratio of sphericalness.
Yep.
And I found it. But wow, that's so funny. Here, by the way, I'm going to share my screen with you. The picture that they made of that Z-axis deformation.
Oh, yeah.
That's pretty darn spherical.
That's spherical, but that also looks like a sea urchin test.
Yeah,
you know?
It looks like a sea urchin shape. I just had a math program graph me a compression ratio of 0.63 to give me like a ball. They had a bunch of different animations in their paper that were really interesting, but I wanted one that looked exactly like what we need. This is pretty close to spherical for life, I thought.
Oh my gosh. I just had a realization. So like I said, this is for a sea urchin, right? The hard shell kind of outer part, but under the spines is called a test. And that comes from the Latin word testa, which means like rounded bowl. They're literally named for being round little guys.
They're round little guys. Well, Adam, the beauty of animation is we can think of whatever world we imagine. So on Roland Safari, those animals would never be able to get rid of all of the body heat they're generating, and that would be awful for them. So even though it's very cute, don't imagine them, actually alive, because that would be horrifying. If you don't have strong cephalization, you end up with a very inefficient form of life for multicellular species. However, that doesn't mean it doesn't exist. There is, of course, enter the echinoderm. So think about echinoderms as the most spherical animal, not those temporarily spherical puffer fish or floofy burbs and borbs. Just think of the humble echinoderm, the cousin of the starfish. No, wait, the sea star? Is that what I'm supposed to say?
Yeah. Now you got it. No angry letters from marine biologists.
Yes, please, no, thank you. I understand, yes. Don't bring your trident here.
Yeah, they're all armed with tridents. When you get your degree, they hand you the diploma and the trident.
Yes, and the one with the biggest trident is the one who's published the most papers, I think.
Yes.
Anyway, the sea urchin. That's the point. The sea urchin. Thank you.
Very cool.
I yield my time.
Now, I think all physics textbooks that say, like, assume a spherical whatever need to have the sea urchin instead. Since that's closest to an actual animal. No more spherical cows in a vacuum.
Yeah, just regular old sea urchins.
Just a little spiky ball out in space. Very confused.
Yeah, don't touch it though, Venom.
Yeah, don't touch the sea.
Don't touch them.
Don't touch the perfect sphere.
Ouchie.
The spiky perfect sphere.
I did read they have a ball and socket joint at the end of each one of those spikes so they can like move them around.
Yeah, they move them around.
Which is so cool.
I'm telling you, echinoderms, I love them so much. Like sea stars, they have, little gills coming up through the skin, and then little finger gills, and then to keep debris from falling on the gills and stopping them from exchanging oxygen with the water, they have like tiny little pinchers on the tops of their bodies that like remove it. They're so cool. They're all so cool.
Weird.
Sea cucumbers, other echinoderms that like vomit their guts at predators to get away. Anyway.
The sea is a weird place, man.
Yes.
I mean, look, I think we can do more than one thing at a time. People are always like, we know more about the moon than the bottom of the ocean, which just isn't true. But it is interesting to me that people think we can only do one thing at a time. We can go to the ocean and see all of these weird things, and we can go to the moon, maybe someday.
Yeah, we can study spherical stars and spherical urchins.
Yeah.
Yeah. Nice.
That's great. Well, on that note, let's wrap up yet another episode of That's Absurd. Please elaborate. Thanks to all of you for listening. This episode was written and produced and whatever else by me, Trace Dominguez.
And me, Julian Huguet.
It was also produced and edited by the wonderful and wonderfully talented, honestly, moderately spherical, but I don't mean that in a negative way. I wonder what his ratio would be. Maybe that's a rude thing to ask. Anyway, Kyle Sisk.
We should get all our spherical ratios checked.
We should.
Where's that math problem?
Let's do it.
What's the equation for that? Let's figure that out. Post your sphericalness. Thanks to listeners who submitted questions featured in this episode. Nick and Adam, if you want to submit questions, look for the form down in our show notes or email us at hello@that'sabsurdshow.com. Visit our website, that'sabsurdshow.com/ask. Call us 302-TAPESHOW, TAPESHO. I think now because of, questions being thrown into the poll on our Patreon, we're getting some like repeat question askers being chosen, not by us, but by the masses. So get on in there, y'all. If you got weird questions, submit away, because some of you clearly have very interesting brains and you're gonna run away. We should make like a leaderboard for who's got the most answered questions.
We need some nerd to help us do things better. So if you know how to do things, send us a message so that we can
make a leaderboard on a Patreon.
Like make a leaderboard on our website. Special thanks to our absurd administrators, Les and Adam, out there looking over, making sure everything's great. So thanks to Les and Adam. If you want to join the Patreon, just go down into the show notes. You can find it there. It's patreon.com/that'sabsurdshow. And we really appreciate all of our patrons. Thank you so much for that, because that is how we keep the lights on. Yeah. Thank you.
And our patrons picked the questions this week, and then spoiler alert for an upcoming episode, we tried to make it so they couldn't make a tie again, and we have another tied poll, so we're gonna have to do another double patron question.
It's coming
episode.
up.
But they all vote on it, and like I said, Win even messaged me, like helping me out, pointing me in a certain direction for my research. So it's real sweet, y'all, that join and support. Like, gives me the warm fuzzies.
Yeah, thanks a lot for that. And if you haven't already, leave us a review wherever you're listening. Give us a thumbs up, a little follow, a little heart, a little check mark, a little whatever, Leave us a review if you want to with words, but at least give other people a notification, a little bit of your information to tell them that we are worth their time. These reviews, these ratings really, really do tell people that the podcast is worth listening to, and we really appreciate every single one of you. We just got an email the other day of somebody who put in a worded review with their actual words and creativity, and they asked us if we could send him a sticker for that, and we were like, heck yeah. So if you want a sticker, not that we're bribing you, go leave a review. Just leave it somewhere, shoot us an email, we'll send you a sticker.
And finally, a special thanks to those listening on Nebula. Nebula listeners get access to ad-free versions of episodes. They support us and other awesome independent creators, including Jade from Up and Adam, who we mentioned in this episode and whose videos were a huge help for me trying to figure out how 1 + 1 could equal 2. That's so frustrating. If you want to join, you can go to go.nebula.tv/that'sabsurdshow.
And remember, Julian, should we tease what's happening next here in our podcast? Should we tell people? I feel like maybe
we tease that at the time this episode will be out, you'll be here in LA visiting me and we'll be filming something?
Yeah. Do you think we should tease that?
I think we just did.
Moving on.
Anyway.
As we say at the end of every one of our episodes of That's Absurd, Please Elaborate every single time.
What is it to? What is 2?
2.
What is
two
it?
Is 2. It's a 2. 2 is a 2.
How did they number the pages before they defined what 2 was? In volume 1. How did they call it volume 1 if they hadn't defined what 1 was until you get 300 pages in?
Is this like a World War I situation?
Apparently,
the first
people
battle
thought it was
of
in
Bull
bad
Run.
taste to call it World War I. They called it the Great War. I'm sorry, I've just been watching Severance, and that character saying that is sticking out in my brain.
Classic.
Anyway, it's a long outro. We should cut down how the thing that we say at the end of every episode, definitely next time.
Yeah, we learned from astrologers that next time someone asks you to do math on a podcast, just add a decimal point to it. That's it. Just add a decimal point and vomit your insides at them, and that's all you need to know.
What is it to?
What is it?
What is it?
We don't know.
I don't know what 2 is.